This is a senior design project for the Mechanical Engineering Department at North Dakota State University. The objective of this project was to design and construct a low-cost hydrodynamic tunnel to serve as an educational and research tool for the Mechanical Engineering Department here at NDSU. Like a wind tunnel, a hydrodynamic tunnel is used to analyze the flow characteristics around an object. Usually, the flow is a scaled-down version of something large. As water slowly flows through the tunnel, lines of colored dye will flow around the object, allowing visualization of the flow. Typically, hydrodynamic tunnels cost upwards of tens of thousands of dollars. For this project, the group must design and construct one for under $3,000. While constrained by the relatively low budget provided, the tunnel is still required to produce a sufficiently accurate, uniform flow in a clear test section, be filled and drained with ease, and produce variable flow speed, all while within a small space within the laboratory. After considering concepts from each group member, a final design was determined. The final design is composed of a system open to the atmosphere with a holding tank, one flow guide, a heart-shaped inlet, clear test section, and a simple piping system. Finite element analysis was completed on the entire design, showing minute deformation on the frame and the tunnel, ensuring the frame is able to support the weight of the tunnel and the tunnel can withstand the pressures from the water. Computational fluid dynamics analysis was completed on the tunnel section of the design. Extensive analysis shows improvements in flow as a result of design changes such as different tunnel shape, an additional flow guide, and cone-shaped inlet pipes. As a result, the chaotic flow of the initial design is, while still not perfect, but drastically improved, producing a much more uniform flow in the test section. The initial design was updated based on the conclusions of the prior analysis. Major changes include switching to a closed system by removing the tank and closing off any openings to atmosphere. This simplifies the design, putting less stress on the pump and allowing the flow to be controlled more easily. Manufacturing of the tunnel then began by first welding and painting the frame. The tunnel itself was cut and shaped by chased steel and then outsourced to be welded. The tunnel and its components and the frame and tabletop were assembled by the group. When the tunnel components were returned back to the lab, a polyurethane sealer was applied to the seams to prevent leaks. In parallel, the inlet pipes were assembled by cutting slits in a large pipe and 3D printing the cones. The whole system was wrapped up by adding plumbing and the glass test section. The same polyurethane sealer was also applied to the corners and the points of contact on the test section. Assembly is completed by inserting the two sets of flow guides, along with aligning the three sections of the frame. Finally, the tunnel was filled and checked for leaks. However, due to complications with the power source, budget, and time, a pump was not added to the system. Future improvements to the system include installing a high-quality variable speed pump, analyzing different outlet designs to perfect the flow, add more components for ease of testing, and lastly, physically testing the tunnel. Special thanks to Rob Saylor for most of the manufacturing recommendations, Dave Savageau for the outsourced aluminum welding, the Mechanical Engineering Department at North Dakota State University, and of course our mentors, Dr. Suzen and Dr. Zhang.